Hi everyone, welcome back to part 2 of the x86 assembly crash course. In part 1, we explored how to read and write this basic x86 assembly code, the different syntax, AT&T versus Intel syntax, and basically we understood how the x86 instruction assembly representation of the x86 instruction works. So today in the part 2, we are going to dig deeper all the way down to machine level instruction encoding. So in today's part 2 of the video, we'll basically break down how actual x86 instruction bytes and understand these notions like what opcodes are, what ModR bytes are, how SIB works, displacement, immediate, etc., etc. This entire video is going to be hands-on. We'll take real machine code example and decode them by hand, byte by byte, so that by the end you will look at the hex term and instantly know which field is opcode and what means ModRM, etc., etc. Okay, so let's dig in. So as I said, this video will be about machine code representation of x86, and in last video we have already seen the machine representation, right? So basically, this x86 instruction can be 1 byte to 16 byte, and the first 0 to 4 byte is basically second. Yeah. So first 0 to 4 byte basically can be the prefix, and then next 1 to 3 byte can be the opcode. Opcode is the required field. The rest are basically optional. Then you can have 0 to 1 byte of which we call mod reg or RM byte, and then optional 0 to 1 SIB, which is scale index base. And then you can have a displacement, which is can be of starting from 0 byte to 4 byte. And similarly, you can also have an immediate value, which can start from 0 byte to 4 byte, right? So this let's focus on this mod reg rm byte. So basically it can be of 8 bit, and I try to mention it like 1 2 3 4 5 6 7 8. So among the 8 bit, the first 2 byte is called address mode bit. So basically it tells you whether it's a register based addressing or memory based addressing or something like that. Then next 3, basically depending on what kind of value you have, it will tell you like what kind of register operand you have. And then the last 3 bit is basically for this, which we call the rm byte. Basically if there is a memory addressing, then what kind of memory address it points to. Similarly, in the scale index base thing, also you have like 8 bit, and they have divided into these 3 things. First 2 bit basically says what kind of scaling you are going to use, and then next 3 bit basically what kind of indexing you are using and what kind of register you are going to use in indexing. And similarly, last 3 bit basically tells you like what should be the base of this scale index base representation. So before we dive into example, let's try to see how depend varying the bit numbers actually point to which kind of addressing mode. So the first thing we call the mod bits, and as I said, we have 2 mod bits in this mod reg rm 1 byte. So it every bit positioning has some kind of meaning, hard coded meaning. So for example, if mod bits are 0 0, then it means that you're going to use some kind of memory operand, but there will be no displacement there. Similarly, if it is like 0 1, so you know again there will be memory operand, but along with the memory, you will have some kind of displacement of 8-bit sign displacement. Similarly, for 1 0, you are going to use a memory operand in your instruction, and there will be a 32-bit displacement attached with it. And at the end, if the mod bits are like 1 1, then you know there is no memory operand, all is register operand. There is this special case we'll also mention next, but still let's highlight it. So if mod bits are 0 0, and your RM bits, basically last 3 bits of your mod reg RM bit, is 101, that means there is no base register. All the address is basically absolute address, and which is mentioned in this displacement section of the x86 instruction. Okay. uh, Moving forward, now we from the mod reg rm byte, we have seen this mod bits. Now let's look at the register bits. So as I said, the register field is basically 3 bits, and depending on what kind of value you have in the reg field, basically you will choose a register. So, for example, if it is 000, then you have an EX register in a 32-bit x86 disassembly. If it is 64, you can consider is equivalent to RX. Then 001 basically for ECX or RCX, 010 for EDX or RDX, 011 for EBX or RBX, 100 for ESP or RSP, 101 is for EBP or RBP, 110 is for ESI or RSI, 111 is for EDI or RDI. Don't worry, you don't have to remember anything. It's just a table. You can, go back and look into it later. Okay. Again, what we have seen so far in the mod deck RM, we look through mod bits, reg bits. Let's look at RM bits, right? So for the RM field, again, you have 3 bits, and it's basically depends on what kind of value you have in the mod bit. So if mod bit has like 1 1, so basically this field will tell you that this is a register and what register to specify, right? And if mod bits are like 0001 or 02, which are like memory addressing mode, then this will tell you what kind of base register you have, whether it is following some kind of scale based index format or not. Okay, so let's look at some example of this RM bit configuration where your mod is not equal to 1 1. That means you are strictly having some kind of memory addressing mode, either with some displacement or without some displacement, or either 8-bit displacement or 32-bit displacement, right? Let's look at it. So when the mod is basically not 1 1, which is 0001 or 02, if your RM bits are like 000, that means your base register is EX. So mod not equal to 1 1 means you already know that this is a memory operand. Now you're trying to figure out what's the base, what's the displacement, etc. So here, if you have like, let's say 01 mod bits and 000 at RM bits, then the base register is EX. So the representation basically here will be something like this. Then similarly, so basically all this number we talked about in the last one, the same numbering mechanism also applies here. So previously also it was 000 for EX. Here also it is 000 for EX, but now we don't use the value of EX as basically some kind of memory addressing. Right. Similarly, for if it is 001, the base is ECX, 010, the base is EDX, 011, the base is EBX. And now there is this special case. If the mod is basically not equal to 1 1 and RM bits are basically 100, then that means that there is some kind of scale index space you are going to use, and which will come next in the instruction, in some next bytes of the instruction. Similarly, if 111, your base is EBP. Now there is a special case. If mod is equals to 0, then and RM bits is 101. That means your address is in the displacement section only. You don't need any base. Else, the base is EBP. Then 110 for ESI, the base is ESI. 111 for the base is EDI. As I mentioned, there is this special case. If mod is 00 and RAM is 101, which I mentioned here, then there is no base. So your address is basically in absolute value in this displacement 32 section. And another special case is if RM is equals to 100, then it is always followed by some kind of scale index base byte. Okay. Okay, now, so let's recap what we have seen, that this is like kind of a machine instruction, x86 machine instruction. We know this is optional, we know this is required, and we look through basically different combination of this ModX RM bytes. Let's try to gather it up and let's try to put a summary of how the effective addressing looks like. Then we'll move to the SIB index. For displacement and immediate, those are basically absolute hexadecimal values, so it doesn't contain anything much complicated there. So now let's combine this mod bits and RM bits basically, and let's try to look at the effective address table like at a single glance. So I have divided it into 4 cases. First thing is case A, where the mod is basically 00, and your so 00 to remember, it was a memory operand information, and there is no displacement, right? And if I have to see the different values of RM bits while mod is 00, it is a memory operand, right? So 00 means it looks something like this, 001 means it looks like this, because these are the base registers, EDX, EBX, and there is this special case. If it is 100, then something scale index base will come after this mod rec RM bit. And if it is 101 with mod 00, it's special case. The whole address is in the displacement, 32-bit displacement value, 110 for ESI, 111 for EDI. Case B, where you have like mod 01, that means you have a memory operand in your instruction and there is an 8-bit sign displacement. Similar to the previous one, now 00 means base is EX and you will have some kind of displacement attached to in the following bytes of the instruction. 001 ECX plus displacement 8, 010 EDX plus displacement 8, 011 EBX, 100 is the special case. That means you'll have a scale index base thing, plus you can add whatever your displacement, 8-bit displacement you have. Similarly, 101 is EBP plus displacement 8, 110 ESI plus displacement 8, 111 is EDA plus displacement 8. Now moving on to the third case where you have the mod bit 10. Again, to reiterate, mod 10 was memory operand with 32-bit displacement. So 00 was similarly, EX is the base register, and then displacement 32 is basically the 32-bit displacement in the memory operand. Same, 001 ECX plus displacement 32, 010 EDX plus displacement, 011 EBX, 100 is the special case, that is followed by some kind of scale index base plus whatever displacement you have in your instruction. 101 is EBP plus displacement 32, 110 was ESI plus displacement 32, and 111 for EDI plus displacement 32, right? Sorry. Now let's move to the last case where the mod is 11. That means we don't have any memory addressing. Everything is like register direct mode. And in that mod, if the RM configurations are like 000, then EX basically have your value. And then for 001 ECX, same as previously, it's just the register direct mode. 010 is EDX, 011 EBX, 100 ESP, and so on. Right? Okay. So again, to reiterate, what we understood is we have, this is how the x86 machine level representation instruction works. You have optional prefix, opcode, followed by 1 byte of optional ModReg RM. Then you have another 1 byte of scale index space. So similar to the ModReg RM, scale will be first 2 byte depending on what value, like 00, 01, 10, or 11. The scale will be like multiplied by 0, multiplied by 2, and so on. And then you'll have some kind of index, 3-bit index. So depending on what the value of these 3 bits are, you will have the similar register configuration we have seen in the ModRM. And then in the base, so depending on what kind of value this 3-bit contains, you'll have like different register. That's it. It's pretty similar to ModRM, ModReg RM configuration. Then you'll have a displacement. Depending on what kind of displacement you need, the value can be up to 0 to 4 byte, and same goes for the immediate value. Immediate values are like when you have like constant representation, constant data in your instruction itself. That's it. Okay, so having said that, let's try to look at a different example. And as I said that these are optional bytes, so let's look at different example. We'll utilize different portions of this x86 machine instruction, right? So yeah, so let's start with the easiest of the easiest, which is basically you only have opcode, which we also discussed in the part one of this crash course, right? So first one is basically no op, and basically its hexadecimal representation is 90, nothing else. So if I have to put this bytes of no op, which is 90 in our x86 instruction, it is just of 1 byte, and all you have is like the opcode 90, which says that please don't do anything. These are just fillers, nothing else. Then for example 2, let's look at an example which has some prefix and opcode attached to it. And one key example is basically this repetitive no op, which is basically used for spin locks. It's like kind of saying this is at this instruction, you are either in a spin lock, or it's like we are at pause until some external event occurs, something like that. So the bytecode representation of this is basically F390. F3 is basically it works as a prefix which modifies whatever opcode you have, and in this case it is like repetitively do no op. Now let's look at a bit complex example where we can utilize opcode, ModRM, and more specifically it is a registered direct instruction. So for example, the instruction can be like move EX and ECX. If you remember, this is an Intel syntax. So the second one will be a source operand, and the first one will be a destination operand. And the byte representation of this particular instruction is 8, 9, and CB. Now, if I have to put this 8, 9, and CB in the x86 machine instruction format we have seen, so 8, 9 is basically the opcode followed by the CB, which is like this ModRM, right? So every opcode basically has some meaning, like what kind of instruction you are expecting, it tells that. So for example, with 8, 9, the kind of instruction it expects, it's a move instruction, and the source operand is actually encoded in the reg bit of this mod RM byte settings, and the destination is basically mentioned in the RM settings of the mod RM bit, right? So let's try to look how to actually decode it if we don't know this assembly instruction. So all we have is like 89 CB. From 89 we know it's a fixed mapping. That's this kind of instruction we are expecting. And if I expand the mod RM byte, which is like CB, which is C for 1100 and B for 1000. And we also know the first 2 bit is basically our mod bit, and mod bit 1 means we know that it's a register direct only, right? We already seen. So we know that something from a register is actually getting passed to some other register, and we know the source register is basically encoded in our reg field. So this is our reg field, which is 001, and we know 001 means our register is basically ECX. Now see, our source register was ECX. And we also know that the destination is a register, but it is encoded in this RDM field, right? If I go to our RDM field, it is 000, and we know 00 is basically for the EX register. So finally, we know this is a move instruction, and something is coming from ECX to EX register. Although I have shown it like from top down, but it was supposed to be like this first, and then from this we decode that, okay, this is a move instruction which is copying something ECS to EX, right? Make sense? So let's move on to a bit more complex example. Now this one utilizes opcode, ModRM, as well as displacement 8. So for example, this instruction like move EX, EBX plus 4. So what it is trying to do? So whatever is there in the address mentioned in EBX plus 4, you copy that value to EX register. Make sense? So if you see the bytecode representation, it is basically 8B, 43, and 04, where 8B is basically our opcode, right? We already saw what 8B does. No, we didn't. So that was 8, 9. See the representation in 8, 9. From one register to RM configuration, another register, it was going something. And in this particular scenario, 8B is basically you are moving, but the source thing is basically mentioned in this RM configuration, and destination thing is mentioned in the R32, that is reg configuration, a 32-bit reg. So if I have to map this particular thing into our x86 assembly instruction, 8B is our opcode, and then we have our ModRM configuration is 43, and this one has a displacement 04. Now, how do I know it's a displacement? I'll mention. Okay. So if I expand our ModRM, which is 43, we'll have 4, that is 0100, and 340010. We know that first 2-bit is the mod bit, which says 01. That means we have a memory operand with displacement 8. And the second reg bit mentioned the destination register, which is 000. That means EAX. And the source is represented by 011. That means if you remember, 011 was like EBX register, and now I have a displacement 8 attached to it. That means this whole thing should represent EBX plus displacement 8. So that is how I know the next byte is supposed to go into displacement because of this 01 mod RM setting. Make sense? Okay. Okay, next, now let's move to similar example, but we are now using displacement 32, right? So we are using opcode, modRM, and displacement 32. So instruction can be something like that. You have move ECX, so whatever value you're having here, you're moving to ECX. So the byte representation of this whole particular instruction is 8B, which is our opcode, then 8D, which is our mod RM, and the rest is this displacement in the backward order. So 7, 8, 5, 6, 1, 3, 4, 1, 2. So 1, 2, 3, 4, 5, 6, 7, 8. That is how you did it, right? So if I have to map it here, 8B is our opcode, 8D is our mod RM byte, and 1, 2, 3, 4, 5, 6, 7, 8 is our displacement 32. Makes sense? So again, let's look at the opcode 8B. We already know what 8B is. It's a move instruction. R32 is our destination register, and the source thing is basically mentioned is this RM configuration. Now, if I expand my 8D, that is the mod RM byte, we'll have 1000 and 1101. We know the first 2-bit is basically mod, and 10 basically says it's a memory operand with displacement 32, right? And this reg thing says the destination register with from this configuration, we know it's a ECX register. See, we have ECX here. And then for the source configuration, we already know there should be a displacement 32, and the value also we know. Let's look at the base registers. With 101, the base register is basically EBP. Now we know what we are trying to do. We are trying to get the value of EBP, adding some displacement, and then we have a memory address. Whatever value that memory address have, we're just moving it to ECX, right? Okay. Let's notch it up and let's throw some scale base, index base thing also, right? So this instruction has opcode, modRM, and SIB together. And the instruction example can be you are moving whatever EDX, whatever value you are having, memory address, the value from the EX, right? And if you look at the byte representation of this particular instruction, it looks like something like this: 8B, 04, 8A. So 8B is the opcode, 04 is our mod RM byte configuration, and 8A is basically SIB. I'll mention how will we know it's in the SIB or it should be in the displacement or immediate section. It is actually encoded in the mod RM. Okay, so from that we know that our destination is some kind of register and source is some kind of RM configuration mentioned. So if I expand 0, 4, basically we have 0, 0, 0, 0, 0, 1, 0, 0, 0, and then 4. We know the first two bits is basically our mod bit, and from 0, 0 we know that we have a memory addressing, but we don't have any displacement. So first thing you know, it's not a displacement. And then the destination register is encoded in 000, which is EX, which also there. And the third one is 100. You remember this was the special case which mentioned that some kind of scale index base is next. So from this, we know, okay, this 8A is supposed to be in SIB, not in displacement. Now let's expand 8A. If we expand 8A, we know the first two bit is basically for scale, which is 4, and 10 is 4, and then you have your index register, which is 001, which says ECX, and then base is 010, which EDX. So basically your whole representation of the SIB goes like base plus index multiplied by scale. Makes sense? And we have no displacement. So this is how you get the memory address, and then you copy the value to EX. Okay? Okay. Now, example 7, and we have a lot of thing going on here. We are utilizing opcode, ModRM, SIB, as well as displacement need. So the instruction looks like this. It's similar to previous one, but now we have a displacement added here. And if we look at the byte representation of this particular instruction, it's 8B 44 54 88. And if I have to map this to this x86 assembly instruction, 8B goes to opcode, then 44 is ModRM, and depending from the ModRM expansion, we'll know which next one should be in SIB, and then the 8 should be in the displacement, right? So from 8B, we know this is the instruction architecture. It's a move instruction. The destination is supposed to be mentioned in the reg bits, and the source supposed to be mentioned in the RM bit configuration. Now 44 is our mod RM, and if I expand this, this is my 4 and this is my 4 again, right? Yes. So we already know first two bits basically mod configuration, and 01 means we have a memory operand with 8-bit displacement, right? And then from reg configuration, we know that our destination register is EAX and our source is 100, which is our special case, that is SIB. So we know we have a SIB, so next byte goes to SIB and then the next goes to displacement. Makes sense? So let's expand the SIB, right? If I expand the SIB, I'll have something like this. This is 5 and this is 4. Now from there, I know the first two bit basically mentions scale, and here it is 2. Remember 10 was 4 and 01 was 2. Okay. And 10 next 3 bits says my index register is EDX, and last 3 bits says my index register is ESP. Okay. So this is how the SIB representation looks like. And remember now we have this 8-bit displacement. So we take whatever we have here and then add it with our 8-bit displacement value. Make sense? Okay. Now let's look at another example. Now this one just utilizes opcode and immediate value, and it looks something like this. You have add EX and this particular number. So basically you do EX equal to EX plus whatever number you have, okay? And if I have to see the byte code and map it to the x86 instruction, the byte code is, this is opcode, and this is basically the whole displacement. So this opcode basically tells you that you are supposed to utilize EX, okay? So this 05 tells you that it's an add instruction where you have EX registered and it is adding with this immediate 32 value, right? So immediate already you have, the opcode you know, and just add it to the UX and store it to the UX. The simple one. Now let me see. Yeah, now we have 2 more examples. There are plenty of other cases, but I'm just covering the ones that you need, like which is necessary for you. The next example uses opcode, ModRM, and immediate 8. So the instruction can look something like this: add EX and like with this immediate value. So if I have to see the byte code looks like this, where 80 goes to opcode, 00 goes to ModRM, 7 is basically your immediate value. Now this opcode says it can be an add or some kind of other instruction where your first thing is mentioned by your RM configuration, and then you have an immediate 8 number. Okay. So if I have to expand the mod RM bit, it is zeros, all zeros. So first 2 bit is our mod bit, and we know this is 00 means memory with no displacement. Now this one is a bit different. Here the next reg field is basically tells you what kind of op code you are going to use. So 000 is basically you are going to use add with this within this 80, right? And then the RM field will tell you what kind of register you are going to use. 000 means EX register, and you have an immediate which is like 7F. Make sense? Now let's try to look at an instruction, our last example, which basically captures everything. So the instruction may look like this. You have a move opcode, and then you have this immediate value, and you're transferring it to whatever memory address this is pointing to. Okay. And if I have to write the hex code or byte code of this particular instruction, it's a very big one, right? And you can clearly see your 5566778 immediate code, and the follow will come. So this is basically displacement. So let's try to map it with x86 instruction format, right? So we know first is basically this is like again a fixed format, 67 points to some kind of prefix, and the opcode is basically C7, and then the next is the mod RM bit, and from the mod RM we will know that okay, it SIB, the next is displacement, which is basically this value, and then the next is immediate, which is basically this value. Now let's try to figure out what it is trying to do. So what this prefix is, so basically this prefix is saying what is the size of the address and overriding it, something like that. So opcode is C7, and what C7 does is it's a move operation. Your source is mentioned in immediate 32, which we already saw, and the destination is from the ModR bit. So let's see how the destination looks like. If I have to expand this ModRM, which is 84, to this particular configuration, we know first 2 bit is basically our mod bit, which is we know from 10 that it's memory plus displacement 32, and we also know our displacement value. Okay. Okay. That being said, then the third thing is okay. Yeah. Yeah. So this is the register, which is this for this particular thing, this 3 bits is not important, that the last bit is actually mentioned. So because of the override, you will know why not to use it. Then the last configuration says that it is an SIB index. So you go to your SIB byte, which is 88. You similarly expand it from the first 2 bit, okay, scale is 4. Then the second one, okay, ECS is index. And the first one, okay, EX is base. So if you have to design this whole memory, it's EX plus 4 multiplied by ECX, right? So let's go back, EX plus 4 multiplied by ECX, and then from our mod bit, we know that it's a plus displacement 32, so plus 10, which is like 32-bit displacement we're mentioning here, right? So this is not it. You have like different variations, different kind of instruction, and different meaning of the prefix and opcode combination, etc., etc. But the code remains the same. So this is how the x86 machine instruction works, and because of this design, it has like variability in the instruction length, and that is exactly why disassembling this x86 representation is a bit hard, to be honest. So This is the end of the video, and that wraps up part 2 of the x86 assembly crash course. And To reiterate what we did, we started with this basic instruction layout, then work out through opcode, ModRM, SIB, displacement, and immediate. And we actually saw the how CPU decodes each field to understand what an instruction actually means, right? I think this is a huge step, because once you understand the byte format, you can decode this instruction on your own without relying on any disassembler, right? And you can instantly just look at the byte, and then you can say, okay, these are the instruction, and maybe you can come up with some kind of optimization based on your understanding, which the modern day compiler is not doing. So in the next video, in part 3 of this x86 assembly crash course, we'll try to see how the stack and the function calling convention work, right? That will wrap up our this whole series of x86 assembly crash course. And after this, you should be capable enough to actually go through the x86 code, and correlate with the C code, or correlate with the source level information, and see how it works. So lastly, if you have enjoyed this video, please don't forget to like and subscribe, and I'll see you in part 3. Thank you for watching.